We have one more speaker in this session before the break. I'm sorry that I don't see your first name. I know that you're Perez, but I don't see the first name.
Angela Perez. Yeah.
Sorry. Will talk to us about single mode bright squeeze vacuum.
Okay. Good morning. It's okay, the sound? Okay, I come from the Max Planck Institute for the Science of Light. I work in the Quadrat group, Division LOIX, and I'm going to show you what I do in my PhD project. We try to study a single mode bright squeeze vacuum and to understand its properties. And actually, this work is mainly how to select it. I'm going to show you 3 ideas we have and how are we implementing them so far. So first of all, what is bright squeeze vacuum? Some of you are already familiarized with parametric in the low gain regime. Just to remind, this pump and the crystal have to be set in such a way that energy conservation and phase matching are fulfilled. And the 2 beams or the 2 photons, let's say in the biphoton regime, they are produced in different angular modes and different frequency modes, and they are called normally signal and idler. And we can set different, we can set different processes in experiment. These processes could be collinear or non-collinear, degenerate or non-degenerate, type 1 and type 2, for example. And okay, we get at the output squeeze vacuum, faint squeeze vacuum, which is represented in phase space, as you see here, ellipse that is a bit squeezed. But when we, okay, here it just passed to collinear, a collinear process, just because we use this in experiment more often. And if we pump strongly, we started producing many pairs of photons that are overimposed one with another. And this is what we call bright squeeze vacuum. It's just high gain PDC, and we have all even photon number states produced after this parametric down conversion. We work in free space, and that's basically what we have. So why is it interesting for us? We know that a bright source that preserves or has non-classical correlations could be used in many, many things. So we have some of them here: enhancement of light-matter interactions through the conditional preparation of large Fock states, for example, or error-free signal transmission, or quantum lithography, increasing of resolution in this case, quantum metrology or quantum interferometry measurements that could be done with more precision. The problem to implement these applications and how to envision these applications right now is limited because of the multimodness of this light. This light is extremely multimode. So we need to select one single mode to work with this. And particularly, for example, in the field of quantum information and communications, is necessary in order to use this kind of light in a let's say, exploit it to the maximum. Because of this multimodness, we need to isolate and control one channel or one mode. This will be the same. So in this direction, we are, let's say, showing today this work. But so far, it's about proof of principle, the ideas we have for selecting this single mode. And it's basically experimental, a selection that is experimental. So what has been done so far? We have some methods. I'm describing here what we use now, what we know. There may be more ways, but let's see. We have 1 and 2 here groups of ways in which we can select a single mode out of squeeze vacuum in general. This single mode filtering can be done in a spontaneous or high gain regime by narrowband filtering, which is a lossy process in general, or by Schmidt mode selection, which in general intends to be a lossless process. It has been done in the case of squeeze vacuum, but Tapster and Rarity experimentally, they could see single mode statistics in frequency, basically. And in bright squeeze vacuum, it was selected, the single mode by absorption of 2 photons, but by the group of Claude Fabre. But the mode after the selection, this is with ultra-fast detection, cannot be retrieved. So we propose here one method in which we can retrieve optically the single mode by narrowband filtering. In the area, or let's say with the method that we propose here, the Schmidt mode selection, Stas Straupe worked in Moscow, and they experimentally filtered from squeeze vacuum one single mode. In our case, we try to do it with bright squeeze vacuum, and already it has been proposed by Christina Silberhorn in Paderborn in Germany. She has proposed another method, but so far it remains being theoretical. We propose here another method, which all of this I'm going to explain in my presentation. This method exploits some crystal separation, and is only done in high-gain regime. This is a method that is, we are the only working on this method. Okay, so here I just show what I'm going to talk about in this presentation. So first of all, just to start, the single mode, how do we in our experiments generally target or know that we have a single mode? We just rely on the single mode statistics so far, because our experiments, I will show you, we basically in our experiment measure the second order correlation function and look at the value of G2 when we have a high number of photons per mode. In this case, I'm just writing here the state, but for twin beams in single mode, let's say 2-mode bright squeeze vacuum. And the idea here is to show, for simplicity, in this system, how the narrowband filtering versus the broadband filtering are performed. So when we do narrowband filtering, we basically want to filter with one pinhole, for example, in angle, one of the modes corresponding to the signal beam, for example. But when we select one of these and we apply the same technique for the idler, we usually will not filter a mode that is matched or is correlated with it. So we can just select part of it, and we will have some light that doesn't get filtered, because these modes that we are filtering are not proper modes of the radiation we have. This is what we call narrowband filtering. Still, we can see single mode statistics, but if we want to preserve or do broadband filtering, matching modes that correspond to the radiation, we have to find a base, which is the proper base for doing it. And we have to find it in such a way that in experiment is possible to filter it by some device. So here, for example, imagine there is a mode that corresponds to the signal beam, and there is the corresponding mode which corresponds to the idler beam. And if we can filter both, and both are conjugated modes, and we have the device that help us to filter exactly what we want, we will perform broadband filtering, and hopefully it will be lossless. So this is basically a hand-waving argument to understand why we want to do Schmidt mode selection. But first of all, let's go to the narrowband filtering experiment that we did before. This narrowband filtering experiment is done in a system which is pumped by an neodymium laser with these characteristics. It's ultraviolet. It's in the picosecond regime. The energy per pulse and the repetition rate here is 1 kilohertz. And what we do is that we focus in between a couple of crystals because of reasons related to birefringence of these crystals, and eliminate the pump and generate PDC radiation, which is passed through a monochromator where it's filtered in frequency, and then the autocorrelation is performed. The narrowband filtering consists in just placing a pinhole, and this performs the angular selection of this light, and this monochromator the frequency selection. And by the monochromator, we can scan the radiation and observe the correlation function. And since we are expecting single mode statistics for collinear degenerate radiation and also non-collinear and non-degenerate, we expect values of 2 in the sides of this curve and 3 in the peak where we have the degenerate collinear radiation. So we have been able to see it. We saw values that are very close to the expected theoretical values. And the drawback of this method was, of course, that even though our beam was very bright and the radiation we got has a number of photons per mode on the order of 10 of 13 photons, we filtered after measurement 10 to the 4th. So we are losing a lot of light. However, okay, this is just to show how that we actually confirm that these are single mode. These are single mode statistics because we measure the photon number probability distributions for these two states. Here will be the signal probability distributions, and they coincide with the expected values. However, the brightness is remarkable. It was 15.8 the gain, and so we are confident that brightness is not a problem for us to achieve. However, the method is lossy in itself. When we want to pass to angular Schmidt modes, as I mentioned before, we want to filter the proper modes of this radiation. We are relying on a method that accounts for the theory related to faint squeeze vacuum state. We deal with bright squeeze vacuum, but we are using so far the theory that corresponds to faint squeeze vacuum in order just to target the region in which we will find or some idea of what are the Schmidt modes of our radiation. So what we do basically is that we consider a system that has the same experimental parameters that we can set in the lab, but for faint squeeze vacuum. And we calculate the two-photon amplitude, of course, and which is given by this, is plotted here, the square of it. And it gives us all the information we need about the state, or we can have about the state. We can retrieve the unconditional probability distribution and the conditional probability distribution as the projection and cross-section of this quantity. And moreover, we can actually use the Schmidt decomposition on it. So we can expand this two-photon amplitude as a sum of separable terms, and we have here the Schmidt coefficients. And it has been shown everywhere that analytically, if we can apply a double Gauss approximation to this two-photon amplitude, it's possible to obtain a base that is Hermite-Gauss. And a base that is Hermite-Gauss has a first mode that is a Gaussian, of course. And experimentally, it's very convenient because there is a lossless filter that is able to filter losslessly this first mode if we are able to target it precisely. So this is the task. And how do we estimate more or less where can we find our, or how can we find our first Schmidt mode? So we know that in the crystal we can produce PDC radiation, which is a non-diffractive limited beam. If we consider two bounds for this, let's say for this beam, one diffraction limited beam that is given by the width of the pump inside the crystal, which will diverge not so much, and another one that has the divergence, maximal divergence of the PDC radiation that is produced by the parametric down conversion radiation, but the waste is much smaller than the pump waste. If we consider these two limits, we will find the Schmidt mode in between. Furthermore, if we apply the idea of given in this paper of Vasilevsky that the first Schmidt mode is the mean geometric of the unconditional and conditional distributions obtained by the two-photon amplitude. So we are able to know more or less what will be, in experimental terms, what will be the Gaussian that we will have to filter out of this, out of our mode, of our radiation. So in narrowband filtering, we perform by putting a pinhole. It's the same idea, and we basically filter part of the Schmidt mode. And if we want to filter the one Schmidt mode, we need to put to use a fiber that exactly gets the Gaussian that corresponds to this mode. The problem in experiment is that it's not easy to know which exactly is the Gaussian that you have to filter. It's in theory one could say yes, I can target some number, but exactly in experiment, due to the fact that we don't have faint squeeze vacuum but bright squeeze vacuum, we need to find it somehow. We need to find the region in which the waste is. So what we do first of all is to envision a method. How are we going to know where it is? And it was found that if we perform a Schmidt decomposition and we have some set of coefficients, Schmidt coefficients and the Schmidt number, we can define some projections of each Schmidt mode on the eigenmode of the fiber. And using these projections, we can know what is the intensity coupled inside the fiber. And from this, the coupling efficiency, know the coupling efficiency. And the coupling efficiency will be maximum when the Schmidt mode is coupled, when the only one projection is present. So basically changing the Gaussian beam that is the PDC that enters into the fiber, changing the size of this beam that we collect, we should be able to target what is the maximum collection efficiency, or where is the maximum collection efficiency that we get. So that's what we do in experiment by the same system. This is, again, narrowband filtering. And here what we do is that we emulate the beam that we want to filter. We emulate the PDC radiation that is producing these crystals, which is drawn here, by another laser, which is overimposed to it. And this laser has the same frequency that the PDC radiation that we are producing. And just varying the waste in between the crystals with different lenses, we are able to maximize the coupling, or let's say set the optical system here in such a way that for each different beam that we could create here with the red laser, we can maximize coupling and then switch off the red laser, turn on our beam in order to generate the PDC radiation, and couple some amount. Where in the beam, or let's say in the location of this beam of the correct Schmidt mode, we will find maximum coupling. Then we just perform G2, which is easy, or just measure the intensity, which is what we require. This is just to show that we have to move the lens just to prepare different beams in the red laser. So this is the first measurement we did because we need to know how many modes do we have originally before the filtering. And this is just done in free space without any angular filtering. And from the G2 measurement, we can know what is the number of modes that we have transversally. And we use basically the information given by the non-degenerate beam, because it's more reliable than the degenerate. And these are our results. The theory shows this, that we are close with the measurement to what we are expecting, but we don't have exactly the peak that we wanted. However, we can recognize a region in which the Schmidt mode is present, and in principle, it can be readily used after setting this waste in the system that collects. What happens with the G2 value? Does it also peak at optimal filtering? So we have done the measurement to see what happens with G2, and for each waist, we perform a scan of the wavelength and the correlation function against the wavelength. And what we see is that the values of the G2, let's say, for example, these points, when we collect better, when we filter less precisely the frequency, which improves our collection, we see that it's a flat value. G2 doesn't really change. G2 is flat. So why does it remains flat after the fiber if we are collecting the Schmidt mode? It's because we can compare the single mode fiber filtering with a beam splitter. We have the independent modes entering to the fiber, and these independent modes have a G2, the G2 corresponding to thermal beams. It has been shown by Giorgio Brida, or it was used, it's a known result that after a beam splitter, these beams do not get mixed, and the output is still a beam with a G2 equal to 2. So the beam is thermal after the fiber, even though independent Schmidt modes are entering. So if we have this analogy, use this analogy accurately, we will have a system of several beam splitters, and we have G2 at the end. It's the same. The second method I will explain very quickly. It just consists on separating the crystals. We are using two crystals in our system because we need to correct for effects due to anisotropy. And this separation of the crystals relies on the fact that our generation of bright squeeze vacuum is a very nonlinear process, and the maximum amplification occurs in the second crystal due to the fact that we have pump. We are generating PDC out of pump, and also the PDC that is generated in the first crystal. So when we move the pump, and this is, for example, the beam obtained after the first crystal and after the second crystal, when we separate the crystals, we are more or less selecting the first Schmidt mode in free space, because we are narrowing the cone that could be amplified by the second crystal. The system is very similar to the previous one. It's just that we are separating these crystals in terms of 10 or 20 centimeters. And what we obtain is that the G2 value goes up, rises with the separation. So we are getting beams that are showing really a single mode behavior. Single mode statistics are appearing here. However, there is an oscillation in intensity, and this is due to interference because of the dispersion of the air and the interference between the PDC that is produced in the first crystal and the second crystal, which have different phase. So as a summary, I have shown you how we implement in technically macroscopic single mode state by selection of a single Schmidt mode from bright squeeze vacuum using a technique that employs a single mode fiber, or by separation of the crystals. We have targeted the first Schmidt mode, at least the region in which it's present, and by separation of the crystals, we have obtained in free space almost the same first Schmidt mode. Our further work will be to measure noise reduction factor, which is basically a measure of squeezing between these two modes in a system of twin beams. So this will be quite a proof of principle. That, however, we are sure we are not going to get noise reduction factor equal to 0, but we expect that it's going to be very, very low. And we have worked in the angular variables so far, so we expect to work in frequency variables and do the selection more accurately in frequency variables also. So thank you very much.
Thank you, Angela. Questions?
Okay. Could you please mention some applications of your single mode state? You are using a squeezed state.
This is a squeeze state because
And
it's,
you heavily select by certain filter.
Mhm.
This, means a strong vacuum invasion and easily, squeeze state could be degraded.
no, this is
It depends on the application, I think. So, what kind of applications?
this is non-classical. Well, it's a squeeze vacuum.
Okay.
It's high gain parametric down conversion light, so it's a squeeze vacuum itself.
So, do you plan to measure some quadrature amplitude after
We
filtering,
don't. You mean measuring quadratures?
like a homodyne detectors
Yeah,
or something?
there is going to be a project related to bright squeeze vacuum and measuring of homodyne detection. At the moment, we don't do this. We use direct detection, and
Okay.
and we are able to measure correlations. So
I see.
we obtain.
I'm afraid that your filtering, is really lossy, I guess, for certain mode. But
okay.
do you have any evaluation of
It's-
some loss tolerance?
The loss tolerance will be evaluated with noise reduction factor, which is this. Of course, the first narrowband filtering is really lossy, but it's not losing at least the correlation
I see.
properties.
Okay.
The second beam mode the Schmidt mode should be better in this sense, and we have a high coupling efficiency, and we see that the signals are huge, much more bright, and still we have the non-classical correlations because we measure the G2 high. But the losses are going to be evaluated in the system because G2 is not sensitive to losses
Right,
actually.
right.
But noise reduction factor is. When we measure the variance of the difference of the
I see,
signals,
I see.
we have to reduce this. We expect to see a reduction,
Mhm.
and yeah. But we hope so far. We have measured squeezing. We have other experiments in which we use squeeze vacuum, and squeezing has been measured out of beams that are gotten by narrowband filtering.
Okay,
So-
and one more. How did you measure the number of Schmidt mode?
The
Did you
number
show the number of Schmidt mode obtained by experiment?
So you mean how many modes do we have?
Yeah.
Yeah?
And how
Yes,
to
yes,
measure?
yes. What we do, okay, in free space, we have this measurement. This
Okay.
measurement is done without filtering.
Uh-huh.
So let's say we are normally setting the level of frequency filtering equal to all, and it's narrowband filtering in frequency. But in angle, we don't filter anything. And what we do is that we expect here a value of 2 normally for single mode, right? So we
Okay.
have 114. And we use this equation here, which is G2 measured is 1 plus the theoretical. From here we get the
I
number
see,
of modes.
I see.
And this is in 2 dimensions.
Interesting. Thank you.
There is time for another short question. Simon?
You concentrated on selection of the first Schmidt mode, but I'm sure there will be applications where you may need to get access to the other Schmidt modes also.
Yeah. Yes. Actually, it has been done for squeeze vacuum. The project that selected single Schmidt mode for squeeze vacuum, which is only pairs of photons, was using a SLM, a spatial light modulator, where we can implement or it's possible to implement any mode from the basis of Hermite-Gauss or a close to basis of Hermite-Gauss. And it's possible to select any mode in principle using a spatial light modulator. We are not doing that because for us it's proof of principle, so we want to select one so far, and the fiber is much more easy to.
What magnitude of single mode squeezing you are using? I mean, you are able to achieve
We have
begin?
not measured really squeezing now. No.
Pardon?
We have not measured squeezing.
You have no measure of
Because
squeezing.
we are using, our process here is collinear degenerate. So we have both singular and idler in one, and we are not measuring in a twin beam system. But this is a squeeze vacuum. So you have pairs of photons, you have the.
Yeah, but how many decibels of squeezing are you able to achieve?
We are not measuring squeezing so far. We rely on the fact this is a squeeze vacuum, and we can see the statistics and the properties that correspond to squeeze vacuum by the correlation, second order correlations, and by the noise reduction factor. This is the the way in which we actually quantify, let's say, squeezing, by measuring this quantity. Variance of the difference. In other projects, usually measure in our lab variance of the difference, and the squeezing is for sure present. But in this project in particular, in Schmidt modes, it has not been measured.
What is the NRF value you are getting for your beam?
What is this? Sorry?
What is the NRF value you are getting for your beam?
This is what we have to measure soon. Yes, this is the outlook. We have so far we measure the statistics of the beam. Yeah, statistics.
All right, thank you very much. Let's thank the speaker again.